One of the two semi-plenary presentations today is given by Mihoko Niitsuma from the Chuo University, Japan. The 60 minutes presentation is followed by a live event that you do not want to miss. The session is chaired by Janan Zaitoun from the University of Reims, who will now introduce the speaker.
Good afternoon and welcome, ladies and gentlemen. My name is Janan Zaitoun from the University of Reims in France. It's my great pleasure to introduce our distinguished semi-plenary speaker this afternoon, who is Dr. Mihoko Niitsuma from Chuo University in Japan. Her talk is related to human assistive robotics for aiding. Dr. Mihoko Niitsuma received her PhD engineering from the University of Tokyo in 2007. Since 2013, she's been working as an associate professor at Chuo University in Tokyo. Dr. Niitsuma is vice chair of the Ifac Technical Committee on Robotics. She was the program chair of the first Ifac workshop on robot control, ROCO 2019. Dr. Niitsuma serves as associate editor of the IEEE Transactions on Industrial Informatics and as secretary of the Technical Committee on Control, Robotics, and Mechatronics of the IEEE Industrial Electronics Society. She also is a member of the administrative committee of this society. In 2008, Dr. Niitsuma received the Best Paper Award from the Society of Instrument and Control Engineers, which was followed by the Best Late Breaking Report Award at the 10th ACM IEEE International Conference on Human-Robot Interactions in 2015. She has co-authored 3 book chapters, 20 journal papers, and more than 100 international conference papers. So, ladies and gentlemen, please join me in welcoming Dr. Mihoko Niitsuma.
Good afternoon, everyone. My name is Mihoko Niitsuma. Thank you all very much for coming today. First, I'd like to thank Dr. Frank Alguva, the president of Ifac, and the organizing committee of 21st Ifac World Congress 2020 for giving me this opportunity to speak here. I hope you all had a pleasant journey here today. This is the outline of my presentation. Today, I'm going to talk about moving toward human-assisted robotics for aiding human activity. First, as a background of our research, I would like to introduce the concept of the intelligent space. Then I'll show you a couple of applications of the intelligent space as an actual example of human-assistive systems. Next, I'd like to talk about human-robot communication for aiding human activities. Especially, I would like to introduce ethologically inspired human-robot communication. Finally, I'd like to discuss the current challenges for human-assistive robotics, such as acceptability of the high-tech systems for wider human users. The first introduction. Let's go ahead and get started. Let's begin with looking at some examples of the use of robotics in real world. It starts with the upper left side. This is an ordinary direction board. When a people wants to get direction information, they need to find this board first. If there were a mobile robot guiding service, the robot could provide direction information interactively anywhere there is a person or a crowd who might need it. Of course, the robot can provide any kind of information, not only direction information. Next example is human industrial robot collaboration. If you have a collaborative robot, the robot helps you with heavy, sometimes dirty routine work, then you can concentrate your own work. The robot can help not only with heavy routine work, but can also help your work cognitively. If you forgot next task, robot motion might help you recall it. Even if you forgot what to do next, the robot will try to proceed with it. If you see the robot motion for the next task, you will notice what to do next. So robot motion can be useful information for its coworker to notice the correct procedure of a task. So, human-assisted robots are not only mechanical machines. As you can see here, many kinds of displays, speakers, and IoT devices are connected to the internet and can also be used as actuators to provide information or services to people. To realize these assistive services using robotics, I would like to introduce you the concept of the iSpace, intelligent space. The intelligent space is an intelligent environment which provides both information and physical support to humans and robots in order to enhance their performance. In order to observe the dynamic environment, many intelligent devices, which are called distributed intelligent network devices, are installed into the environment. Sensing and computational functions are implemented not on the robot, but in a space, as shown here. Through the distributed sensors, the intelligent space can perceive and understand events in the whole space and share the information with robots through the internet. In addition to observation, intelligent space actuates intelligent agents such as mobile robots, computer devices, and digital equipment. Therefore, intelligent space can be recognized as a platform for the implementation of robotic systems and processes to provide assistive services for humans in the real world. Here, I'd like to show you the observation function as one of the basic functions of iSpace. iSpace has basic functions to observe the position of people and robots and describe the observed information as an environmental map. By indicating it on the map, the information can be visualized, which is useful for human users. And iSpace can share the map with the robots. Then the robot can obtain information of the position of human and the robot, obstacles, and the usage history of the space. Here is a demonstration video. Let's see the demonstration video. This is a bird's eye view of the floor. The brownish colored area are recognized as a static object. The other colored objects are moving objects. Here, we used two 2D LiDAR sensors as shown here. We get distance information on the object around sensors. The distance information refer to where the edge of the objects are, as shown here. Therefore, we generate points to represent the edge of object where distance information has been obtained. By evaluating the distance between points, we extract each object from the point data, then distinguish moving objects from static objects. Finally, we get the environmental map as shown here. This green color represents the history of object movements, which means the frequency of human activity in each area. In the latest environmental map building system, in addition to the history of movement, walking direction and changes in velocity and acceleration are also obtained. The figure on the upper left side is the original environment where we observed. In this case, 3 2D LiDAR sensors are used. This figure shows a map of walking direction. Walking direction is presented using corresponding colors as shown here. This figure shows a map of average acceleration of human walking. And this figure shows a map of visit frequency of humans. If you have the map of the human walking direction, you find the large green colored area as shown, as you can see here. This map presents that this environment is used to pass through from north to south. On the other hand, if you go toward the side, there are some spots colored red. The color red means no movement. If you look at the picture of the original environment, you can find that there are some tables and chairs around here. So we could expect that some students are sitting at tables, and actually they did. This is also confirmed from the map of visit frequency history. We can see darker colors in locations where people are lingering. What is important here is that the map enables robots to obtain information about how people use this environment. Starting quite recently, these maps are being used to observe and evaluate people locations and flows in various kinds of environments, for example, offices, shopping malls, and parks. Then, environmental design will be updated based on the objective observation data. The environmental map is used to plan a path of a mobile robot. Basic information of the map is the location of a static object that will be obstacle. The robot planned the path to avoid collision with obstacles. In addition to the obstacles, the visit frequency history is presented on the map. These areas are colored because people often go through these areas. We could expect it that this area is often used by people because it is efficient or convenient for them. If a robot wants to choose an efficient path to choosing an often used area might be a good idea. Or if a safer path is more desirable, the robot can plan a path to avoid highly visited area like this, because the possibility to encounter human on the path can be reduced. As you see these examples, intelligent space is very useful and powerful solution to build a map of the whole environment. Here, I'd like to introduce an autonomous guidance robot as one of the examples of assistive systems based on the intelligent space. To realize this, one of the most challenging parts is how to find the person who might need a guidance. In other words, we need to consider that how the robot can find a person who does not know his or her destination or does not know how to get there. To solve this problem, we applied the environmental map, including history of human visit. Referring to this map, the robot can know which areas are often visited by people and which areas are not used very often. Basically, we can recognize that there is less reason in the white areas for human to come or stop there. So if a human is standing in a white area, probably that person does not know his or her destination. In addition to the location where people used, we focused on the shape of walking trajectories. If a person knows a direction to the destination, the walking trajectory might be straight, like this. Therefore, if not, we could expect that the possibility that the person is looking for a destination might be high. Based on the ideas, we implemented computational model to determine a person who might need a guide. The system is based on environmental map, working trajectory, classification, and mobile robot navigation. Here's an example of the experiment of assistive robot. 3 sensors are used for this experiment, as shown here, 1, 2, 3, and there are 2 participants here. Each participant has each task. A task of a participant is to look for a specific object from the object on the tables. This means that that person does not know how to get there. On the other hand, the other participant knows where she should go to do her task. Let's see the demonstration. Could you find a person who might need a guidance? Okay, I hope your answer is the same as the robot. So let's see the movie again. So the robot determined that this person needed a guidance, and it approached to the person. And the robot asked the person whether she needed help or not. Then she answered yes. The robot showed her destination by moving there. So this is a demonstration of an autonomous guidance robot. And this system consists of the whole processes of iSpace, intelligent space, from observation, recognition, and actuation. Let's move on to the next example. This is another example of assistive systems based on the intelligent space. In case of human-robot collaboration in manufacturing, safety is not enough. The robot should be safe and productive. Then we introduced the new concept called responsible robot. The system consists of a Kinect sensor for the observation function, a dynamic and proactive decision-making process combining the observation process and recognition process, and the industrial robot. In this system, a 3D map structure is used to describe human working history in this environment, and it is used for the risk estimation. Then we implemented a risk assessment model based on the human's location and the location and posture of the robot. Here, the human-robot separation is evaluated. Let me show you a demonstration of human-robot collaboration with a responsible robot. The system was run in teach mode during the experiments for safety. This area is defined as a shared working space, and this is the storage. The robot has 3 tasks. So first one is a refill the Lego bricks bin with a Lego bricks using a box of Lego bricks from storage, and supply the human operator with empty box from used Lego bricks from storage. And the last one is a collect a box of used Lego bricks from human operator and place it in storage. The system calculates the likelihood that the human operator will be visiting a shared workspace within the time the robot needs to execute a task in that shared workspace. Then the robot proactively selects a task and acts to ensure the safety of the human operation and maintain the productivity. We confirmed that the system reduces the average number of human-robot conflicts in the collaboration, and the robot was able to perform the necessary number of tasks to be productive. In addition, the experiments demonstrated that the responsible robot reduced the workload for the human operator. I would like to introduce another application of intelligent space. This slide shows the system called Spatial Memory. The Spatial Memory is a human interface in iSpace. Different kinds of equipment are connected to the intelligent space network, so users of intelligent space can use them. Usually, each device has its original user interface, as shown here. Therefore, users need to select an appropriate user interface to operate the devices. I thought it's not convenient for the users, so we have proposed the spatial memory as a unified user interface to enable users to operate different kinds of devices in a unified way in intelligent space. In addition, when retrieving the digital data in computer, you need to know the name of files. At least you need keywords to search it. What if you cannot remember any keywords to search a file? It might be difficult to retrieve the file. Then we focus on the use of real world. Can you remember the bookshelf in your office? You might be able to remember the brief arrangement of your books on the bookshelf. You can find the intended books without exact name of the book. So we decided to use the real space to store digital information and digital command to operate devices based on human spatial recognition ability and memory of body motion. The spatial memory system stores the digital information in association with the location information in the space. Then iSpace gets the position of human and recognize the body motion. Users can directly access saved data or execute saved command using body position. This is a demonstration of the spatial memory system applied to Robotics Technology House at the National Institute of Advanced Industrial Science and Technology at Tsukuba, Japan. These spatial memories are created to operate the window and the blind. In this system, the Kinect sensors are used to observe the position of human. Let's see it. So iSpace observes the position of users, and when the hand stops, it tries to retrieve the stored data from the spatial memory based on the position of the hand. If there is a spatial memory stored, the data will be retrieved and executed. The sensors and all devices capable of running spatial memory data are connected in the same network. Let's see again. The user accesses the red circle, the doors open, and when the blue circle, doors closed, and the user can close the blind by accessing yellow command, and he can open the blind using green command. This is one example of the spatial memory system. This is another demonstration of the spatial memory at RT House. In the previous demonstration, a user accessed the spatial memory actively. In this demonstration, embedded spatial memories are passively accessed by a user via necessary activities. Okay, let's see it again. Please look at the door lock. When the user is sitting down to take off his shoes, he passively accesses the command to lock the door key. And when he left the entrance hall and entered the living room, he passively accessed the command to turn off the light, and then the light was turned off. Let's move on to the next topic. Here, I would like to discuss what is a challenge for providing assistive services using robots for people. Let me consider the situation that a robot is going to guide a person. The approaches of guiding a person using a robot can be divided into two ways. One is guiding a person using a robot based on the person's request, and the other is guiding a person without any request from the person. There is a big difference between the two situations in terms of human-robot communication. When a robot is guiding a person based on the person's request, the person has realized the purpose of the robot behavior, and the robot already got the person's attention before it starts the guidance. The person and the robot reach the consensus on the guidance. Then, the robot would likely be successful in providing guidance. On the other hand, when a robot is guiding a person without any request from the person does not notice the intention of the robot behavior, and the robot needs to get the person's attention before the guidance. So that's why the robot behavior needs to be designed so that it seeks the person's attention and shares the purpose of the robot behavior. This is an issue of human-robot communication. To address this issue of human-robot communication for human assistive systems, we are proposing a concept of ethologically inspired human-robot communication. We consider the issue as design on nonverbal communication between a person and robot. Here, it would be desirable if a person user can communicate with a robot without a lot of training. Then, we focus on human-dog communication. Because they don't use common language but are living together, dogs' behaviors can be interpreted based on experiences. Therefore, we have proposed the approach of robot behavior design based on ethologically described dogs' behaviors. And we call the approach as Etho-robotics. Here is a demonstration of ethologically inspired human-robot communication. The robot shows preferences to human users autonomously. Could you name the behavior of the robot? Or could you guess which persons does the robot feel familiar to? Let's see it. Okay, here is the answer to the question. The answer is attachment behavior. The robot behavior is designed inspired by the dog's attachment behavior, and this person is recognized as the owner of the robot, and the other person is recognized as an unfamiliar person to the robot. There are some ethologically described dog's behaviors, such as the attachment behavior and leading behavior. The dog's behaviors when communicating with humans are described. The attachment behavior model has been obtained through the experiment called strange situation test shown in this video. The behavior model can be applied for the robotic agent to show social relationships with human users. So there is an owner and a dog in an unknown environment to the dog, and now unfamiliar person enters the room. So ethologists observe the behavior of dog according to the situation and describe the dog's behavior, then obtain the behavior model. The leading behavior has been obtained through the experiment called hidden food test. The leading behavior can be applied to realize a guidance assistance. I'll show you the details later. Ethologically inspired design of robot behavior means that translation of the ethologically described model into the computational behavioral models. That includes design of behavioral factors, design of proximity, and design of motion. Here, the design of proximity and design motion or design of trajectory is very important to present the intention of the robot as a nonverbal communication. Let me show you another example of the robot behavior inspired by the attachment behavior. The shape of the trajectory emphasizes the tendency of the robot intention that it wants to avoid unfamiliar person. So as you can see in this video, the shape of the trajectory is very important to describe the relationship between the robot and the human users. Let's move on to the next slide. Here, I would like to introduce the leading behavior. This is a good example of simple ways of communicative interaction between a dog and human. And guiding people is one of the useful mobile robot applications. So we focus on the dog's leading behavior. Dogs can bring a person to a location where they want to go by using only nonverbal communication. The model of the leading behavior is obtained from the experiment called hidden food test. Please look at this picture. So there is a hidden food in the shelf and dogs find it, but the dogs cannot get hidden food by himself. So that's why the dog wants to bring someone to get hidden food. The reading behavior is observed in this situation. The dog's reading behavior consists of 3 behaviors: attention getting, showing direction, and gaze alternation. The attention getting is the behavior to get the attention of the person. As a showing direction behavior, dogs show its intention toward both the target person and target position. Gaze alternation behavior is showing the target clearly near the target position. Let's see the demonstration of reading behavior. This is the target person, and the robot tries to get the attention first and showing the direction to the target person and target location. And near the target location, it shows the gaze alternation behavior. This is the whole processes of reading behavior. This figure shows the movement path of the robot and the person in the reading behavior. This is the target position to go, and here is the position of the person, and here is the initial position of the robot. The red line shows the path during the attention-getting behavior, and blue line shows the path during the showing direction behavior. In the attention-getting behavior, the robot generates a non-straight path toward the person. If the robot goes directly to the person and just turns to the target position in front of him, it is difficult for the person to notice the intention of the robot, that the robot comes to the person to get his attention. So it is important that the person is able to notice that the destination of the robot is his or herself by seeing the robot movement. Therefore, the robot trajectory is designed to make the robot approach to the person from the direction of the target. These are examples of effective paths and non-effective paths as attention-getting behavior. The figure on the left-hand side shows the example of effective paths, and the right-hand side graph shows the example of non-effective paths. In this case, the robot moved toward the middle of the person and the target directly and turned to the target. In this case, it was difficult for the person to notice that the robot tries to get the attention of the person. We tested the usefulness of trajectory design through the experiment, and we found that the shape of the trajectory was very important to get the person's attention. Long-term communication is one of the most important issues in human-robot interaction, as many literatures suggested losing interest in a robot over time is a problem. Although the attachment behavior can be useful to maintain the person's interest in a robot, it is not enough to develop the relationship between the person and the robot. Some literature suggests that each person has a different preference for the behavioral characteristics of a robot. The behavior of the robot should be changed based on the human-robot relationship. From this, we can say robot behavior should be enough informative to find a difference in behavioral characteristics based on human-robot relationships. To express the difference of behavioral characteristics, 3 factors are introduced to Etho-robot: the degree of attachment to the owner, degree of familiarity to non-owners, and degree of sensitivity of anxiety. To represent the relationship between the robot and non-owner but familiar person, the degree of familiarity to the person should be high. On the other hand, to represent the relationship with a non-owner and non-familiar person, the degree of familiarity to the person should be low. The robot behavior should be modified to show different behavioral characteristics. More specifically, robot motion, including proximity and trajectory, should be designed based on the three factors. In addition, we need to consider how to update the behavioral characteristics representing the relationship between humans and a robot. The relationship with non-owners should be updated if the person uses the robot repeatedly. The degree of familiarity should be changed based on not only their interaction history, but its quality. There are two references to update degree of familiarity. The first one is a direct effect. Direct effect is to directly evaluate non-owner's reaction to the robot. If the non-owner person shows negatively or violently behavior to the robot, the degree of familiarity should be decreased. The second one is a social referencing. The social referencing is to evaluate the relationship between a non-owner person and the owner. For example, the owner stays close to the non-owner, which means the non-owner can be trusted. So that's why the degree of familiarity to the non-owner can be increased. Here, I would like to show you an experiment to evaluate whether the robot behavior is enough informative to find a difference in behavioral characteristics and recognize the relationship between a person and a robot. There are the three conditions as shown in the table. The first condition, if the robot has a fixed low degree of familiarity to the robot to non-owner, the robot will show the very negative behavior to the non-owner. It might look like not social and not friendly behavior. In the second condition, if the robot has a fixed high degree of familiarity to the non-owner, the robot will show very positive behavior to the non-owner at the beginning of the communication. It might look like very positive and very friendly behavior. In the last condition, if the robot is able to update the degree of familiarity to the non-owner, the robot behavior will change from negative behavior to positive behavior. Here is a video of the human-robot communication to be tested here. Could you expect which behavioral characteristics of a robot is shown from the three conditions? Please take a look at this video. We prepared the videos for the experiment, and each participant watched the videos and answered questions. The first question is to find the owner of the robot and the non-owner of the robot. The second question is shown in the slide. The how do you think the robot feel about non-owner person? 20 subjects participated. Here's the result of the experiment. All participants found the owner of the robot correctly. Results for the questions how do you think the robot feels about non-owner are shown in here. The answers can be classified into 4 groups: accepted, interested, afraid, and not interested. Then the result is shown in the ratio of those groups. When the robot had a fixed low degree of familiarity to the non-owner, the human subject perceived the robot felt the non-owner afraid or not interested. When the robot had a fixed high degree of familiarity to the non-owner, some of the subjects recognized the robot would not be familiar with the non-owner, even the robot showed constantly friendly behaviors. On the other hand, when the behavior characteristic was updated based on the interaction with the subject were able to interpret how the robot felt about the person almost as expected. Therefore, the behavioral characteristics should be updated based on the interaction between human users and the robot. Okay, let's move on to the last topic. Here, I would like to discuss one of the current challenges in human-assistive robotics. First, there is an issue of acceptability of robotic agents. The question is it enough if the robot is very functional and very productive? Even if a robot agent has very useful functions, it won't have any opportunity to assist human users if the human users do not accept the robot. Our approaches to address this issue are the study on the attachment behavior of the robot and the study on the social touch with the robot. These behaviors represent relationships between human users and the robot and empathy to them. Here is one example of social touch between a human user and a robot. So this robot is called Pepper. It has cameras and mics and the capability of facial expression recognition. We implemented the emotional estimation model based on the facial expression, and the Pepper proposed a high five based on the result of emotion estimation. The experimental result shows the possibility that the acceptance of the robot was increased when the Pepper showed the high five with the users. I'd like to talk about the effect of social touch in another opportunity. In this presentation, I would like to some result from the experiments with attachment behavior as a social behavior of the robot. In addition, evaluation of the acceptance of robotic agents is another challenge. One of the approaches is stress assessment in human-robot communication. I would like to show you a monitoring assist system with the Etho-robot. This system consists of Etho-robot showing the social behavior inspired by the attachment behavior, and an iSpace-based environmental map building system to detect unexpected persons' invasion to a blind spot. The Etho-robot received a notification of the unexpected person invasion in the blind spot from iSpace. Then it shows a situation to the user. Here's a demonstration of the monitoring assist system with Etho-robot. Please take a look at this video. This slide shows the experimental result of human-robot communication using the monitoring assist system with robot agent. 12 subjects participated. In this experiment, each subject stayed in iSpace with a robot for 30 minutes for 3 days. Here, there are two conditions. One with the Etho-robot showing social behavior inspired by the attachment behavior, and the other one with non-Etho-robot showing just functional behavior to notify emergency. This figure shows the score of the subjective evaluation for the non-Etho-robot, and this table shows an overview of questionnaire items. As you can see in this figure, there were no significant difference in most of the evaluation items. Even the human subject spent time with the robot for 3 days. However, the score of the intention of use was significantly decreased on day 3. Okay, this figure shows the scores of subjective evaluation when using Etho-robot. As you can see here, when the robot showed social behavior to the user, the subjective evaluation were improved over time in most of the evaluation items. And especially intention to use and perceived enjoyment and perceived ease of use and social presence are significantly improved during the experiment. So social behavior might improve acceptability of the robotic agent. So further investigation is our future work. Let me show you another example of human-robot collaboration. In this experiment, the collaborative robot and human user collaborate to arrange a set of same-colored tableware on the trays. The robot picks a cup up and places it on the tray. A human collaborator will arrange the same-colored other tableware on the same tray. To achieve stress-free and efficient collaboration, we designed the auditory cues for human operator. In our previous study, it was observed that human subjects felt stresses from high-speed robot motion and unpredictable robot motion. So, auditory cues are presented to make a human operator predict robot motion. More specifically, auditory cues present a robot target object. The direction to the target is shown using binaural volume difference. The depth to the target is shown using different frequency of sound. The sound is designed based on our previous study. We use bone conduction headphones to present auditory cues. Bone conduction headphones convert sound wave into vibrations that can be received by the cochlear directly, and thus a human operator can hear both auditory cues and surrounding sounds. Presenting timing of auditory cues is also important. If the timing of the presenting cues is inappropriate, then the human collaborator will get confused and the fluency of human-robot collaboration will decrease. Related studies revealed that presenting cues before the robot moves toward the human decreases the mental stress of humans, and time range of 1.0 to 1.5 seconds before the movement corresponds to the ideal timing for presenting cues. From this, we present auditory cues of 1.0 to 1.5 seconds before the robot movement. and the maximum speed of the end effector is selected based on the ISO standard for the safety. We conducted experiments under the two conditions, one with auditory cues and one without cues. 12 subjects participated. The efficiency was evaluated based on the task completion time. The task completion time is defined as the amount of time measured from the moment that robots start moving to a cup until the last tableware touches the tray. The graph on the left-hand side shows the mean task completion time. The mean task completion time was significantly reduced when the auditory cues are presented, as you can see here. The graph on the right-hand side shows the mean response time. The response time is defined as amount of time as measured from the moment the robot starts moving to the target until a human subject touches a first tableware corresponding to the same colored item that robot grabs. As you can see here, the mean response time when using auditory cues was also significantly decreased. This means that the human subject predicted the robot target color and started moving before the robot moved. From these results, the presenting auditory cues improved predictability of the robot motion and improved the efficiency of collaborative work. We also evaluated each subject's subjective evaluation of human-robot collaboration, how human subjects perceive the collaboration with the robot in terms of fluency, robot contribution, trust, and so on. We used a 7 Likert scale to evaluate each item. This figure shows the Likert ratings of the perception of human-robot collaboration. The collaboration with auditory cues tended to be rated higher or better than the collaboration without cues. The differences of the ratings of robot contribution, trust, discomfort, and predictability were significant when the auditory cues were presented. This slide shows the result of stress and mental workload. Galvanic skin response, GSR, is observed to measure the objective mental stress, and subjective mental workload is measured using NASA TLX. When participants were ready, they experienced a 2-minute period of rest to measure GSR, and then started the collaboration task. After that, immediately after each task, they experienced a rest period of 2 minutes to measure GSR. Then they completed a questionnaire on perception of collaboration and NASA TLX. This figure shows the result of GSR stress level. As you can see here, there was no significant difference in GSR stress level between two conditions. Also, this figure shows the result of mental workload measured by NASA TLX. Also, there was no significant difference except performance in the mental workload. From these results, we found that auditory cues did not affect human subject stress and mental workload. Here, I'd like to summarize the discussion about current challenges about human-assistive robotics. The result from the recent research reveals that social behavior of the robot improves subjective evaluation of robotic agent of the assistive systems. and interface which present assistive signals to human users for human-robot collaboration improves efficiency and perception of the collaboration. And presenting assistive signal did not affect human subject stress and mental workload. Today, I presented some achievements of our research aiming toward human-assistive robotics. Robot technology with high functionality and high productivity will appear. And I believe social skill design based on Etho-robotics will harmonize human-robot collaboration. Finally, I'd like to thank my students and collaborators in Hungary for their contributions. And thank you all for listening. It was a pleasure being here today.